Okay, so the second example is of asteroid 1627 Ivar, and the images here are provided from Thomas Kluak. In this case, there are 3 nights of data. Each night has several hundred, actually in this case, this first night has 855 images, so it's quite a lot of images, but they're each only 2 seconds in duration. In contrast, the previous example, there were 60 images the first night and 50 the second, and they were all 120 seconds in duration. So it's a bit of a difference. In this case, again, exposure times are much shorter, but you have a lot more images to work with. And so let's go ahead and take a look. We don't need to, for this purpose, just to take a look at the images. It won't show all of them, but maybe just a handful here. So, of course, these are the raw images, and they have not yet been aligned. The background level is not normalized yet. So we'll go ahead and perform the normal processing routine. So we go to batch mode, and again, this helps to automate the reduction process. So here we have 3 sets of images for this asteroid. So I'm going to select them, and of course the auto run configuration is the same as before, and I've decided to actually use for this case PixInsight for the alignment. It's another option here, so I'm going to click OK, and I will click begin, and so it's off to process the data for each of the 3 nights. So we'll go ahead and let it do that, and then return once it has finished processing the data. Okay, so it has finished processing the 3 nights of data, so we can proceed to generate photometry measurements of the images. But of course, first we need to load up the orbital element information. So here we go to download observations of this particular asteroid. I could actually just type in Ivar if I wanted to do so. And so I click OK, and then it will download the observations. So we give it a moment because it's somewhat of a larger file, I suppose. Okay, and so it has returned the observations, and honestly, if you want a bit of a shortcut here, most of these asteroids that have observations that span decades, you can actually tend to simply cut back to maybe the past few years of observations, and that way you get a quicker determination on the orbit. It should be, for our purposes, just as accurate as otherwise. So go ahead and let FindOrb compute the orbit, and once it has done so, then we can proceed with applying the ephemeris information to the data set. So okay, it has finished doing that. And of course we have to change our observatory to the one that acquired these images, so we do so here. So that is now the active observatory, and now we can attach to the data set. So 1627, that's the instance that we want. I opened that just 39 seconds ago. Of course, well, it has elapsed more time now, but anyway, I click OK, and again, the columns have been populated, and so the object is expected to be in the field of view, so that's good. So I'm going to go ahead and view images. Again, this is starting with the first night of images. Here we have 830 images that made it through the processing. So I'm going to click view images, and we wait for it to load. Again, 830 images is a fair number of files to process. Okay, so once it has done that, then we can proceed to create a stack with ephemeris information. And this will form the starting point for our track. So I'm going to double click on the object. And by the way, I forgot to mention this in the previous example, but we do have the aperture settings here. So if you go to display aperture settings, you can actually update the size of the aperture used for the measurements. So if I want to, I can size this appropriately. So maybe a target radius, in this case of 6.4 pixels, might be appropriate. That way you can fully enclose the target within the target radius circle. So you can adjust it to your liking. Here I might say 5.7, that would be fine. So I click OK, and anyway, I'm going to go ahead and proceed with creating a track. And so again, the idea here is that we will then be able to generate observations from this track, but again, from ephemeris information, you might not have the most perfect track established, so we can go ahead and get a slightly more accurate one here. So I create the markers, and I explained this in the previous example as well. So this gives us our second track here that has been refined from the first one, and then I load star catalog, and now I proceed to create observations. So we're going to do 830 observations, and so we go ahead and click Add Observations. So again, the 1627 IBAR, and we go ahead and let it generate these observations. So we'll give it a moment to do that. Okay, so as before, I am going to select all of the observations and copy them to a new photometry set. So as you see here, again, we have two new windows appear. First one being the list of photometry sets, which we have just one so far for the first night, and then the list of measurements for this particular set. So as you see here, 830 photometry measurements have been taken. So as before, if we wanted to, we could go ahead and graph the data, but first I'm going to save it to the repository. Again, it's always a good idea to continually save your work and progress. Okay, so we can go ahead and plot the data, and this is what we have for the very first night. And if we want to, we can examine this option here. So by default, it is going to exclude outliers from the data. Normally you want that, but if you wanted to, you could uncheck that and then see where it might have some of these outliers. I should have clicked OK there. So here we have some of the outlier data points here. I can go ahead and go to plane so you can see this. And so if we want to, we could look at those data points as we go through them in the measurements here. So if you look in this column here, the magnitude uncertainty is populated, and sometimes that can give you some idea as to whether or not a data point may or may not be valid. So here's one, for example, 2.5. That's quite a high uncertainty, and sure enough, the measured magnitude is certainly quite different. So sometimes you can definitely get some idea from this magnitude uncertainty column as to whether or not a data point would be thrown out. So if we wanted to, we could delete that data point, as well as these others here that also have high uncertainty. And so we can just continue to do that. So certainly, and here's one as well. But you don't really have to do this necessarily, since the tool automatically throws out outliers. But I'm just going to do it here for this example. So I can delete those. And if I replot the data, and I didn't get rid of all of them, but just to show the update on the graph. So now it looks like we have only a few outliers here. So we took care of most of them, and if I wanted to, I could actually just drag over these two data points and then right click and delete. So it's very straightforward, and now we have a nice clean looking graph of the data. So I will go ahead and save this modified graph here. So these 808 points. So we had 830, now we have 808. And so again, it looks like that. And of course, we can change the title of the graph now to reflect the asteroids we are currently working on. So at this point, I will go ahead and process the other 2 nights of data, and we can go from there. Okay, so I went ahead and generated the photometry measurements for the second night, and I thought before I went any further, I would go ahead and show how you could clean up the data in a fairly straightforward fashion. So here we can just plot the selected graph. Again, if you plot both, then you'll have obviously both of them plotted. But if we're just working on the one photometry set, we can just say plot selected, and it will give us just that one data set to work with. And so here, of course, as before, if we want to clean up outliers and so forth, we can do so. So easy way to do that, again, you actually just drag over and choose delete, and then we can clean up the data that way. So I'm just going to go ahead and do that here. And so I will do the similar thing for the third night as well. But that certainly cleans it up, and now I will save that. And now move on to the third night of measurements. Okay, so here is the third night of measurements. There are almost 1,000 data points for this one. So if I plot the third night here, you can see that there's actually, the data is actually quite clean. It looks like we only had one outlier this time. And so just out of curiosity, I would like to know which data point that is exactly. So if I go to photometry measurements and I inspect the columns here, it looks like maybe it's this data point here. So it's saying magnitude 19.95. Certainly that's not correct, but it did that only on one. But if we look here, this is the result of that. Okay, so it appears that somehow or another, maybe the alignment routine or maybe the camera even just simply output this kind of image here. So that's obviously garbage data. We don't want that. So again, all of this is really not necessary. We don't really have to delete this data point here, because if we wanted to, we could just simply go back to the normal setting here, exclude outliers. And when we do that, it automatically takes care of outliers in that case. So, but just because I want to, I might as well delete that data point. And there we have it. So that is our third night of data. And I'm going to save what do we have so far. And so at this point, we can then proceed to do the period analysis. Okay, so as I mentioned in the previous example, when you want to do period analysis, you need to attach the object data. So we right-click and choose Apply Object Data. And again, this works quite similar to when you apply ephemeris information to the data sets. So I'm going to select this instance of Find Orb. Again, I've just kept it running in the background, and I click OK. And again, there are thousands of data points here, so it takes a little bit while longer, but it went ahead and did it. And so all of these thousands of measurements now have the information attached to them. And so what we can do is plot all of the data sets here. And here we can go ahead and choose light time correction. So it's not much change in this example because it's not an asteroid that's very close to us. And also I can choose absolute magnitude. So that made a bit of a difference there to normalize the magnitudes. And then finally we can go to the period analysis. Okay, so here's the period search window as before. So I can specify the start and stop as well as the number of steps to take. And so this asteroid, just since we might as well know, it has a rotation period of 4.795 hours. So that fits within the start and stop range here. And we'll go ahead and try it with 800 steps. So I'm going to click Find Period. And here are the results returned. So periodogram here indicates this is the period spectrum, and it looks to me like we have 4.8 is the first period returned, so that's very close to the 4.795, and here it is on the phase plot. If we wanted to, we could increase the number of steps by tenfold, and it will take a little bit while longer, but here now we have the 4.795 exactly. So that's quite reassuring, and it's very helpful now, especially once we have all of these thousands of data points. We can measure this period very precisely. So we have a very good result here, and this did not take very long. This, as they might say, is a somewhat simpler asteroid because it does have a higher amplitude. So amplitude here is 1.03, but for this example, I say it's a bit more involved because, of course, we had a lot more measurements. So each measurement was only a 2-second exposure time, and we had thousands of them. So it is for the processing side of things, it takes a lot of work and effort. But as you can see here, we're able to use software that can help to automate a lot of the processing for us. So at this point, we can say that we now have a light curve of this asteroid. We've identified the period and its amplitude, and that is a good result. Okay, now before I move on to the third and final example, I thought I would show just a couple more options we have here with the software. So we do have the ability to export these data through the ALCTA format. So that enables you to share it with others who have other programs that can import this formatted data. So if we do this export, then it will ask you for some contact info, location of observatory, and so forth. I'm just going to give it some default values here. When I click OK, it's going to then ask for a file name. So these are always just plain text files. So I click Save. And if I wanted to, I could then import that data. So for example, I could delete all of these here and then import what I just saved as a text file. So if we were to open this up first in Notepad, for example, you can see it has the header information for the ALCTA standard. So this is what that looks like. So you have object number 1627, name, and so forth, and then you have the actual data itself populated by Julian date, magnitude, and the uncertainty of the measurement. So being able to export that is helpful, and then of course also being able to import it is also helpful. So as you can see here, I just imported a file that was in the ALCTA format, and let's take a look and see if I am able to apply object data, and then once I do that, if I am then able to compute the period as I did before. So light time correction, absolute magnitude, do a period search, and then we see what the result is. So sure enough, I imported ALCTA file. I was able to add touch orbital element and then compute the period. So very simple and very straightforward.